Look at this. Absolutely gorgeous. Just feast your eyes on that for a second. It contains millions of tiny glinty particles. It looks like a real photograph of a high-end jewelry store, doesn't it? But, believe it or not, this is not a video recording. This is rendered on a laptop, and it is running in real time. Usually, when we see sparkles like this in computer graphics, they are either fake, pre-baked images, or they completely melt your graphics card. But this is simulating the actual physics of light hitting microscopic scratches. It is fluid, it is dynamic, and it is happening right now, calculated fresh for every frame you see on the screen. What a time to be alive! Now, if you have ever looked at a sparkling surface in a video game, maybe snow in the sunlight or metallic car paint, you might have noticed something annoying. It usually looks, well, a bit like static noise on an old TV, or it looks like a flat plastic texture with white dots painted on it. When the camera moves, the sparkles shimmer the wrong way. They crawl across the surface like ants. Why is that? Because simulating millions of microscopic mirrors is a nightmare for computers. It is one of the hardest problems in rendering. But today, we have a paper from the heavy-hitter scientists at Adobe and NVIDIA that tackles this head-on. It is stable, incredibly fast, and the best part? It is free for everyone to learn from and build upon. Before we dive into this wizardry and explain how they tricked the computer into doing the impossible, I have a small favor to ask. If you enjoy unpacking complex topics like this and want to survive the AI revolution with us, make sure to smash that subscribe button right now. It really helps the channel grow, and I am lucky to have you fellow scholars on this journey. Every comment and like pushes these ideas to more curious minds. Ready? Let's dive in. Okay, but how? Why is this so hard? Let's break it down. Imagine a surface like the casing of your phone or a shiny car. To you and me, it looks smooth. But under a microscope, that smooth surface is actually a chaotic mountain range. It has micro-roughness, tiny scratches, pits, crystalline structures. When a beam of light hits these tiny mountains, it does not bounce back perfectly like a mirror. It hits a jagged microfacet and reflects in a very specific direction. Each one of those aligned reflections creates a tiny flash. We call these flashes glints. Now imagine there are not 10 of these, not 1,000, but millions, even billions across a surface. Each one capable of producing a sparkle depending on the angle of the light and the viewer. That is a combinatorial explosion of possibilities. And computers, as powerful as they are, still operate under tight time budgets. In real-time graphics, you often have about 16 milliseconds to compute everything for smooth 60 frames per second. That is not a lot of time to simulate reality. So usually, in computer graphics, we cheat. We blur it out to make it look smooth and shiny. We use statistical models that average everything into a soft highlight. Most of the time, it is good enough, but it is boring. We want the sparkles. We want that rich, high-definition reality where individual glints pop in and out as you move. The problem is, if you try to render every tiny scratch explicitly, your computer screams. You get aliasing. Because pixels are tiny squares sampling a continuous world, if a sparkle is smaller than a pixel, the computer gets confused. It turns on, then off, then on again as the camera moves. You get flickering fireflies, unstable noise. It looks like a broken glitter lamp shaking violently. So, how did the geniuses at NVIDIA fix this? Hold on to your papers, fellow scholars, because here comes the genius part. To solve this, the researchers used something called importance sampling. That sounds technical, so let's use an analogy. Imagine a nightclub party inside a single pixel. In the old method, we act like a terrible party promoter. We invite everyone. We send light rays randomly everywhere inside that pixel to see if they hit a sparkle. But most of the time, they hit empty space. We are wasting computing power calculating darkness. This new technique puts a smart bouncer at the door of the pixel. He has a clipboard with a VIP list. He knows where the cool kids, the sparkles, are likely hanging out. This is what the paper calls a hierarchy of distributions. Instead of guessing randomly and hoping to hit glitter, the algorithm builds a structured probability model of where glints are likely to appear. It narrows the search step by step, zooming into promising regions and ignoring empty space. It is like using a treasure map instead of digging randomly across a beach, or like a metal detector that only beeps for gold. The result? It converges incredibly fast. It is far more efficient than blind guessing. Calculations that once required huge sampling now happen smoothly in milliseconds. And because the sampling is guided and hierarchical, it remains stable as the camera moves. No more glitter chaos. But wait, there is more. This is a game changer for artists. Usually, to put a texture on a 3D object, you need UV mapping. Imagine taking a chocolate bunny and trying to flatten its foil wrapper onto a table without tearing or wrinkling it. It is impossible. You get seams, distortion, stretching. And for an artist, that means hours of tedious manual work, cutting the model into pieces, flattening it, painting carefully, hiding seams. No thanks. This new method is intrinsic. It works directly in 3D space. It does not rely on flattening the surface into a 2D map. Instead, it defines the sparkle structure mathematically inside the material. It is like the sparkles are baked into the substance, like chocolate chips in a cookie, rather than printed on top. That means you can have effectively infinite detail. You can zoom in forever. Since it is procedural, driven by mathematical rules rather than fixed images, it never pixelates. It simply evaluates the function at a finer scale. The closer you look, the more structure appears. It behaves more like a real physical material than a painted illusion. And this brings me to a little thought. This technique works because it does not store a static image of sparkles. It stores the rules for creating them. That is powerful life advice. Stop hoarding isolated facts. Stop trying to memorize the UV map of life. If you only memorize data, you are limited by your resolution. When you zoom in on a new problem, you run out of detail. But if you learn principles, the underlying rules, you become procedural. You can adapt. You can generate solutions on the fly. You maintain your dimensionality. You are not replaying stored textures. You are computing new answers. Do not be a 2D texture in a 3D world, fellow scholars. Be the algorithm. Be the bouncer with the clipboard. Now, is it perfect? Almost. The authors note it is not strictly energy conserving in every extreme scenario. And because it performs sophisticated math in real time, it is heavier than a simple plastic shader. So if you are running this on a very old machine, you might struggle. But for modern GPUs and gaming systems, the visual payoff is enormous. The realism jump is immediate. You go from fake glitter noise to believable, stable microstructure that responds naturally to light and motion. The trade-off is worth it. So let's recap. We have a technique that tackles the long-standing glitter disaster. It runs in real time. It uses hierarchical importance sampling to avoid wasting effort. It frees artists from tedious UV mapping. It enables procedural, infinite detail sparkle materials. And it reminds us to learn rules instead of memorizing snapshots. That is a lot from one research paper. And the best part? You can experiment with it yourself. No supercomputer, no complex installation. Just open the demo in your browser and start playing. Rotate the object. Zoom in. Change the lighting. Watch the glints dance realistically without exploding into noise. I spent 20 minutes just spinning a dragon model around, mesmerized by how stable the sparkles were. I regret nothing. This is the kind of progress that makes computer graphics feel alive again. Not just incremental tweaks, but smarter sampling, better abstractions, deeper respect for physics. Thank you so much for watching and being part of this community of curious minds. If you want more deep dives into cutting-edge research like this, make sure to subscribe. Also, check out the description for product links and gear I use to make these videos. It genuinely supports the channel. What a time to be alive! I will see you next time.